Nuclear physics. The atom is the building block of all matter. It has a nucleus with protons, neutrons, and an electron cloud outside the nucleus where the electrons are orbiting or moving. Depending on the element, the amount of electrons differ as well as the amount of the orbits surrounding the atom. I want to talk a little bit about energy levels before we start talking about the atomic structure. Something interesting happens when electrons travel from one energy level to the next. If an electron is excited, that means the energy is absorbed, therefore a photon will be absorbed, and the electron will go from inner circle to an outer circle. If an electron is de-excited, it means that the photon will be released and the electron will jump from a higher energy level to a lower energy level. We call these leaps from energy level to energy level quantum leaps. Since a photon is emitted, that means it must have a certain wavelength. Now let's talk about nuclear components. Nucleus contains nucleons, protons, and neutrons. Atomic number Z defines the number of protons in an element. Neutron number N defines the number of neutrons in an element. Mass number A is actually the number of nucleons contained in the element itself, which is the sum of Z plus N. Each element has a unique Z value. And notation-wise, this is how we're going to write elements: X, A, and Z. Isotopes of elements have same Z's, but they can have different N and A values. Nucleus charge and mass. So a proton has a charge plus E. Its mass is 1.672 times 10 to the minus 27 kilograms. Its atomic mass is 1.0 in AMUs. Mass in MeV over C squared is 338.28. Neutron has a neutrally charged. Its mass is 1.675 times 10 to the minus 27. Its mass in AU is 1.00866. And its mass in MeV is 939. Electron has a negative charge. Its mass is 9.1 times 10 to the minus 31. Its mass is 5.48 times 10 to the minus 4, and its mass in MeV is 0.51. So compare the masses of protons and neutrons. They're about close to about 900, whereas the electron mass is a half of a unit. The unified mass unit U is used to define carbon-12. The mass of one atom of carbon-12 is 12 U. 1 U is equals to 1.66 times 10 to the minus 27 kilograms, or 931.4 MeV over C squared. Scattering experiments are used to determine the size of the nuclei. They are measured in femtometers, and 1 femtometer is 10 to the minus 5 meters. Nuclear stability. An attractive nuclear force must balance the repulsive electric force, called the strong nuclear force. Neutrons and protons affected by the strong nuclear force. There are 260 stable nuclei, and Z number has to be less than 83 for a nuclei to be stable. Above that, it is not stable. Binding energy. Total energy of the nucleus is less than the combined energy of the individual nucleons. The difference is called the binding energy, or mass defect. So delta M will be the sum of the masses inside the nucleus minus the mass of the nucleus. Radioactivity. Unstable nuclei decay to more stable nuclei. They can emit 3 types of radiation in the process: alpha particles, beta particles, or gamma rays. Alpha particles are basically helium nuclei. Beta particles are electrons or positrons, E+. Gamma rays are high energy photons. The way we detect these particles is by putting them through a magnetic field. Each of these particles, because of their charges, will deflect in certain ways, as shown here. Alpha particle through a magnetic field that's pointing inwards will tend to move upwards. Gamma particles, since they are neutral, will not be deflected, and electrons will bend downwards. Decay rate, or decay activity, is the number of decays per second. Lambda is the decay constant. The unit of decay is Curie or becquerel. Decay is exponential. Half-life is the time that it takes for 1/2 of the sample to decay. So 1 Curie is about 3.7 times 10 to the power 10 decays per second, and 1 becquerel is 1 decay per second. So R, which is the decay rate, is delta N over delta T, which is equals to lambda N. Or N equals N naught e to the minus lambda T, where N is the initial number of particles. So if you were to look at this decay curve, what you see is N naught is the number of initial particles. As time goes by, it decays to 1/2 and 1/4 and so on. Now let's talk about certain decays. So let's start talking about alpha decay. Alpha decay is unstable nuclei emits an alpha particle, for example, like basically a helium nucleus, spontaneously. Mass of the parent is greater than the mass of the daughter plus alpha particle. And most of the kinetic energy is carried away by the alpha particle. So that reaction looks similar to this. So whatever particle you have, X, A minus 4 will be given to the helium and Z will be Z minus 2. So what are some of the applications of alpha decay? Well, Americanium-241 is an alpha emitter used in smoke detectors. Alpha particles ionize the air between the gap. The small current is passed through that ionized air. Smoke particles from the fire enter the gap, reduce the airflow, which sounds the alarm. Beta decay. Beta decay involves the conversion of a proton to neutron, or vice versa. It involves the weak nuclear force. The kinetic energy carried away by the electron or electron-neutrino or positron or positron-neutrino pair, as given here. So a neutron will decay into a proton plus an electron plus an antineutrino, or a proton will decay into a neutron plus a positron and a neutrino. In general, this decay will be given by this. X, which is a particle which is decaying, will equals Y, A, Z plus 1, or Z minus 1, as the case may be, as it is here or here. So, applications of beta decay, there aren't many real applications of beta decay other than beta voltaics, which make batteries from beta emitters. Beta decay, however, very importantly, led us to the discovery of the neutrino. Now, beta plus decay. So isotopes which undergo this decay and thereby emit positrons include carbon-11, potassium-40, nitrogen-13, oxygen-15, fluorine, and iodine-121. So if you have a particle, a nucleon, then basically it's going to emit a beta plus or a positron and decay. This reaction is basically given by this equation given here. Now beta plus decay applications are very, very important. For example, the PET, or the positron emission tomography, is a very, very well-known example of a beta plus decay. It is used in nuclear medicine as imaging technique which produces a three-dimensional image of a functional process in a body. The system detects pairs of gamma rays emitted indirectly by positron-emitting radionuclide or tracer, which is introduced into a body on biologically active molecule. Gamma decay. Following radioactive decay, nucleus may be left in an exciting state. That nucleus further undergoes a nuclear de-excitation and protons move to the lower energy level. Nucleus emits a high energy photon. This one, because gamma has zero charge, there is no change in A or Z. Now, gamma ray applications. Gamma rays are the most dangerous type of radiations, as they are very, very penetrating. They can be used to kill living organisms and sterilize medical equipment before use. They can be used as CT scans and radiation therapy as well. One way to detect stowaways inside a truck is by using gamma rays. This technology is used by Department of Homeland Security at many ports of entry into the U.S.